this is what you have to know for the final exam also. So we talked about it. You have learned to use cross-correlation to get the time lag between two signals in the time domain, right? Cross-power spectrum is the frequency domain equivalent of cross-correlation. And since you have convolution in cross-correlation, in frequency domain, convolution becomes multiplication, right? Because of that, cross-power spectrum is simply the FFT of S1 times the FFT of S2 conjugate. Because if you wanted to do this in the time domain, you would calculate cross-correlation. If you calculate the cross-correlation in frequency domain, you multiply the FFT of one by the conjugate of FFT of the other one. And the result is a complex vector. So S1, 1, 2, last time I called it SR1R2 following Sohail's paper. It is a function of frequency and it's a complex valued function.
So I'm sorry, so you're saying that it's the FFT of signal 1 times the conjugate of the other one?
Mm-hmm.
Okay, so...
This is a MATLAB. I write it as if I'm doing this in MATLAB.
Okay.
The conjugate is that star on the top.
So what's the other...
That's just multiplication in MATLAB.
Okay. I just don't understand why there's like two... Like the one on top
because
is denoting that that's the...
You can, I can take the MATLAB notation out and just put like that. If this is better. But in MATLAB you have to do that. Okay. So, here is the cross-power spectrum. And now we are looking at the phase. It's a complex valued function. So if you look at its phase, of course it's a function of frequency. This is what we are going to get. What is the graph at the bottom, coherence function? Why do we have that? Did we, let me check. I'm just trying to check if I, oh, okay, this is the last thing we have talked about last time. Okay. So we have talked about it. The coherence function shows us how well correlated are these two functions. It is equivalent to what in time domain? A little bit of energy. What is the equivalent of coherence function in?
Self-correlated.
No. What does self-correlated mean? Autocorrelation, you mean?
Yeah.
No.
It's not that.
No. What is coherence function? So coherence function, we also talked about it last time, that you take the cross-power spectrum and you divide it by the product of, we call those auto-power spectrum. So we have cross-correlation, autocorrelation, cross-power spectrum, auto-power spectrum. And that means simply cross-correlation of a function with itself. That means that instead of multiplying FFT of S1 by S2, I'm multiplying FFT of S1 by itself. And this is a number between 1 and 0. If the two functions are very well correlated, it becomes closer to 1. This is like cross-correlation coefficient. Remember what you were plotting to see where the maximum is to get the time lag? I want everyone to make this connection between time and frequency domain in your, right? So this is what it is. This is the first part. Mathematically, you know, what that is. And conceptually, now, what do they show? What is cross-power spectrum is showing? This phase is showing the phase shift between S1 and S2. The phase shift between the signals recorded at one receiver and the other receiver. This is the concept. And the concept of coherence function is how well correlated these two functions are. So, for example, you can put a threshold and say if your cross-correlation coefficient is less than 90% or 0.9, then this part of data has been very noisy. So you just ignore it. You don't bring it into dispersion curve. And in practice, this has a lot of implications. So you weigh your phase with coherence function. If the weigh is high, it becomes significant. If the coherence function is low, that part of the phase you don't use. So this is what I wanted you to write down. Now, how it is being used to calculate velocity? I think from here on it is simple. So if we have the phase, what should I do to get velocity? What's the procedure? Spectral analysis of surface waves. What's the procedure? How do we get the time delay out of... Exactly. So you take this and divide it by 2 pi f, and this gives you this delta t, the time delay that you need. Right?
I'm sorry.
And this is as a function of frequency.
So the phase of that would be like the...
This is the phase shift. So whatever we get here is the phase shift.
So like for
So if you divide the phase
like,
shift,
about like 150 degrees.
100 and this
So
is
for
180 times 2, 360.
I mean for the numerator.
So this is 180 and times 2 is 360 in degrees.
I'm asking for the numerator.
Yes.
Like what would be the input? Like for point A it would be like 150.
But we'll get there. This is the first part. So for every single point here, if you program it, now I didn't want you to do any programming. I'm just giving you 3 points. But in reality, you have to do every single point. So for every point, you know what the phase is. You divide it by 2 pi f, and you get the time
I'm just
delay.
asking the phase is just an angle in degrees.
Yes, it can be degrees or radian.
Okay.
It's a it's not phase. It's like it's phase of power spectrum. It's really phase shift. It's like your lag in cross correlation. That's not time. That's lag time.
So do we know the value for that?
Yes. So let's. We haven't talked about this part. This is the value. I mean, that's what we have. This function that you see on the top is. So just to tell you that in the exam there is a question where you have to do this in MATLAB. Right? And since we don't have a homework, that's why I'm explaining this very, very clearly. Again, what we are looking here is the phase of power, cross-power spectrum. And the phase of cross-power spectrum is the phase shift between the two receivers as a function of frequency. Okay.
I just want to make sure I understand, like, so if I'm just looking at the graph, I would just say it's like maybe like 160 for point A.
Yeah, I mean, now you have to just, I'll explain, it's not 160, I'll explain how to, I've explained it last time, but I'll show you numerically how it works. But if you have the graph for every point, you know exactly what it is. So you have to program it. You basically divide it, just like that. You have everything. So you have a vector where you have phase values, and you just divide it by 2 pi times that. Yeah? This is how a spectral analysis of surface wave works. Any other questions so far? Now, one more step before going to part B. To get velocity, then we have to divide the distance. So the phase velocity, we divide the distance by this. And of course, it also becomes a function of frequency, because for different frequencies, you have different arrival times. So that's how you get phase velocity. And typically, you plot this versus wavelengths, which will be your velocity over frequency. Sometimes people also plot it versus frequency. If it's not specifically stated, either one works, but typically wavelengths is preferred. Okay. Any questions? I mean, this part is clear, what is going on in SSW. Okay, now, I put these numerical examples because I thought it makes it more tangible. So I'm asking now, let's look at only 3 points, A, B, and C, and basically calculate the points on the dispersion curve corresponding to these 3 points. For A, what is the phase? Right. So the most important thing here, there is a step where you have to unwrap the phase. So here, last time I showed you that you basically unwrap it. In one question, in homework number 1, I've asked you to do that long time ago. And now I have to, ask you to look back and see that you use just a simple MATLAB command, and it unwraps the phase. What does unwrap mean? Means, you basically, this 360 degrees, you go here and then you add that, you unwrap the phase. And this is what you get. The phase you want to put in your equation is the unwrapped phase, because that's how many time has taken, how many degrees or radian has taken. Now, if this was given in radian, you would put 2 pi. Now it is in degrees, so you have to divide it by 360, right? So the phase of point A, this one was already given to you here. So it is like 980.
I don't understand why I see that it's 300.
So this is like about 80. So you can say 1, 2, 3. That's 330, and this is 100. You could go from the other side, 2.5 plus 100. It would be fine too. So you can either way, but it has to be unwrapped phase. In the exam problem, you need to use unwrap from MATLAB. So you have to really do this automatically.
Excuse me?
Yes?
Should the unwrap phase be negative or?
No, it is positive.
Which
So
is
you
kind of on the positive.
exactly. Good question, so. So tell me what is at B. What's the phase at B? How much? It's 180, right?
Oh yeah, I'm sorry.
So it goes from 180 to, it goes from pi
Yeah,
to
zero to
negative
100.
pi. Yeah. How about C?
3 times 360.
Exactly. This is all degrees. Now we have to calculate delta t. That means for each of them, you divide this by 360 by f. So we also need to know what is the frequency at every point. At A,
32.
yeah, I have 32. This is like you have to eye it, so it may not be perfect. At B,
35.
frequency?
9, 7. Oh, I'm sorry. Oh, 7. Yeah.
I have like 6.
Yeah.
You can have 7 if you want. I have my numbers for 6. And at C, is everyone following Hingjun? You know what we are doing?
No, not really.
Okay, I guess that. Okay, we up to here it's okay.
Yeah.
Okay, now for every point, we have to calculate the time shift. So the time shift comes from dividing the phase by 2 pi f. And f is the frequency at that point. No. So if we go here, look at point A, you just read what is the frequency. And then B and C. Jiyoung, everything is okay?
Yeah.
And at C?
That was 35.
Oh, okay.
Yeah, I mixed it up, yeah.
Yeah. And now you have the formulation going from phase. So calculate, please, the delta t's. Actually, do I have it? Yes. Check that my numbers are okay. I get numbers like that.
I don't see how you're saying it's like 6.
I'm just going from B down and kind of.
Alright, I guess it's just. Oh,
It's
these are-
7.
these
Use
are
7.
diversified, and
Yeah, this is not
significant.
very accurate. I think it's a little bit larger than 6. You're right, but this is what I have written for myself, so it's not. Okay, the velocity, so the phase velocity corresponding to each point would be just 10 meter divided by this delta t. And then if you do that, you get different numbers.
Why this velocity is so small? This velocity
They're so similar.
is so small.
Oh, because I just took 10 meter. I actually couldn't find in the paper what the distance has been. And I took 10 meter, just like that. I'll show you the dispersion curve. When you look at, this is what they have. The phase velocity is very small. So I try to choose a number where we get phase velocity which fits. This is from the same data. It's earth material. I don't know why it is so small. Yeah, it's probably unbound soil, something. Or maybe it was just a numerical test. I don't think so. I think it's real data. Yeah, it's a really soft soil. So I try to see what should I choose for the receiver distancing to get something which fits the numbers I have here. And I came up with 10. So now we are not done. To get dispersion curve, you also have to have either frequency or wavelengths. To calculate wavelengths, you also need the phase velocity. Pay attention here. The wavelengths also is a function of phase velocity. So to get wavelengths, you have to use the phase velocity that you have and divide it by frequency. And then, of course, the dispersion curve is the plot of phase velocity versus wavelengths. It doesn't matter if x and y are reversed, etc. You can sometimes have frequency here, and then you have a few points. So this was what I expected you to do for the quiz. No, the idea was more that we do a homework in the class that you don't have the chance to do before your exam. Now, you need to still submit your quizzes at the end of the class. But look here. So this is the dispersion curve corresponding to the whole data. We only looked at 3 points. If you program this and look at every single point that you have, you are going to get a full dispersion curve. So if you want to kind of show where we are, you know, we kind of, point A falls somewhere here. Point B is 20, is, let's say, somewhere here. And point C is also very close to point A. So this is what this whole thing means. Okay. I hope that this helped you, to understand the process a little better. So I already told you that one of the questions in the exam is a very, very simple, 2 very simple signals, but you just need to do this.
So we need to use MATLAB to
Yes.
get the unwrapped.
Exactly. And please, I have written on the exam also, don't include your codes. I only want to see the graphs. But include the graphs. Okay.
I didn't write the explanation of question 1 on this. I wrote it on this. When I have this in.
Please add it at the end and give it to me.
Okay.
Yeah, sure. I mean, this is not about this. A graduate class is not about grades. It's about what you live with afterwards. If it helps you in any ways. Okay. Now, once we have the dispersion curve, something that we won't really go to the details is inversion. Similar to tomography, then you kind of have to start with a model. You see the initial model here. You get the initial model, you generate a dispersion curve for that initial model, you compare it to the experimental dispersion curve, and you do it as many times as the dispersion curve, the model, and the measurement, they are similar to each other. And then that final model would be the model of the velocity profile that you were looking for. Yeah.
How do we get from shear wave velocity to phase velocity to an inversion curve? To compare it at the end.
How would we get from there? So we have a dispersion curve. This is clear how we get it.
Yes.
Okay. To get a dispersion curve, typically it's not enough to have one set of receivers. You need to have, the rule of thumb is that if you are probing like 15 meters, you need to have receivers who are 15 meter apart. And I told you that the distance between receiver and the first source and the first receiver is typically equal to the distance between two receivers. That means that you need to repeat the test for different spacings, and then you put all the data points together to get a dispersion curve through the procedure that I showed you. So now, what is the question?
I don't understand the whole idea of inversion.
Oh.
How do you get from shear wave velocity?
No, you don't get to shear wave velocity. You want to get, okay.
Yeah.
So inversion is similar to tomography. You start with the initial model. You just assume that you have some change in velocity with depth. Okay. Then you have to do forward modeling. So we can write it down. Initial model. When I say model here, that means velocity, shear wave velocity versus depth. So you assume this is the initial model. How do we decide on that? You have some information about your site, and you have some geological maps. You don't know anything, you just assume something. Whatever on the surface, you assume it's going all the way down. It's as simple as that. Then you do forward modeling, that's numerical modeling. Just like tomography. And you do forward modeling. When I say forward modeling, I mean that you assume you have this kind of material, you assume you have this source, you assume you have these receivers. You record numerically what would be the response in every receiver. And then, as if these were real data, you do dispersion analysis. You get dispersion curve. You do SSW. And then you compare your dispersion curve versus your experimental dispersion curve. So you compare it with experimental. And there will be a mismatch if your model is not correct. You use this mismatch to correct your initial model.
Isn't the one that we're actually doing the initial model is just a theory?
No. Initial model is not a theory. It's initial values. It's an assumption. This is in any inversion. This is if you do any kind of inversion. This is how it works. You start with a set of results, with a set of expected results. You assume something. So you think that would be your answer. No matter what type of inversion, this is always the case. Okay, and then you take that and you calculate the response of your system based on that initial assumption. When you get the response, you compare that versus the real response that you have measured. And you use this mismatch to correct your assumptions. And you repeat it as many times as this mismatch becomes minimized according to a certain rule. This is like a general procedure of any kind of inversion.
But is the velocity that we're comparing from the dispersion is phase velocity?
Right.
The one that we initially assumed, is that also phase velocity that we assumed?
No, we assume shear wave velocity.
So how do you bring that connection together? How do you get from
If you
phase
know-
velocity to...
If you know shear wave velocity, I've taught you how to calculate Rayleigh wave velocity, and you know this with depth. So it is shear wave velocity profile. It's not just shear wave velocity. If you know this with depth, you can calculate dispersion curve. You know the wavelengths of each frequency, so you can very easily calculate the dispersion curve. Normally, you don't do it by hand. You do it by numerical modeling. You don't see how?
Even in the last lecture that we had, I always had the problems with how we got from shear to dispersion. I think you can just write a, I don't know.
Sure. I mean, it's good that you ask when something is not clear. Yeah, I remember you were asking questions about this. So you have wave velocity 1 and 2. Can we just focus on 2 layers for now? So imagine that I assume this wave velocity. Now, this is written Rayleigh wave velocity, but this could be also shear wave, right? Because if I assume a Poisson's ratio, then I immediately get Rayleigh wave. Everyone agrees with that? Okay. So you have this. Then you want to go from here to dispersion curve.
So I'm sorry, so what's the purpose of the dispersion curve? It's just showing us how the phase velocity is changing as our frequency is changing, but like, so like.
Can I please finish answering Mahbouba's question, because she has asked this, and then I will come back to your question. So now we have this assumption we want to go to dispersion curve. This is wavelengths. Okay. Now normally you do simulation, but let's say we don't do simulation, just conceptually. As long as the wavelengths is smaller than the first layer, I have assumed the thickness also, right? I assume the profile. Then I can say that the velocity will be Vs1. That's the shear wave velocity for layer 1. Yeah. And then once we start going to the second layer, it will be a combination of Vs1 and Vs2, depending on how much of my wavelengths is inside layer 1 or layer 2. And since the second layer is lower velocity than the first layer in this case, it kind of smoothly becomes smaller. And at the end, if we go deep enough for larger wavelengths, this will be Vs2. Because the effect of it becomes so large that most of it is in Vs2, so the effect of Vs1 becomes minimized. Is it clear? So now, normally we can't do this by hand. It's hard if you have multiple layers. So what you do, you numerically simulate this. So you put here a source numerically, and you record the response at several locations. And then you use SISW to get the dispersion curve. Just like I showed you, you calculate cross-power spectrum, you invert it, and you're going to get that. But for 2 layers, this is how it is. Is it more clear now? Yeah. So.
Sure. How can we connect the wavelengths to depths?
Because of what you know about surface wave velocity, we know that we know exactly how for each frequency, we know that this is what is happening. So you know that when the wavelength is about 1 point, even in reality this is about 1 wavelength. You know that the effect of this layer will be minimized. We normally don't do it by hand. Okay, we use a modeling software, but this is the basic principle.
So why do we have dispersion happening? Just because we have another layer beneath it? Is this based on just like reflection and refraction? Or no, like why does this happen that it starts to have different, the way I understand it is like you have different components breaking off into their own velocities.
Why dispersion is happening? So one way is just the graph I just showed you, to think about it this way, for Rayleigh wave. Just that dispersion happens because the motion of Rayleigh wave is confined to about 1 wavelength. So if you are probing with a lower frequency, larger wavelength wave, it's going to go deeper. And this wave is traveling through 2 materials. So its velocity on an average becomes affected by 2 layers, right? But if it's a small, it's within the small layer. Now, answering your question that if this has something to do with reflection and refraction, The answer is yes. And that's the last thing of this class. This can become very complicated, so that's why I started just with Rayleigh waves. But Rayleigh waves are only special kind of plate waves. So look at here. If we have a free plate, you have this slide, no? So you are right. Dispersion happens in reality because of multiple reflection and refraction at the boundary. This is the other way to actually look at it. So the last part of the surface wave, I just want to, as much as I can, I want to bring to you the whole picture. So Rayleigh waves are only a small part of what is happening on the surface of a medium. So the reality is, if we just look at a plate, so this is just a plate. When you have a plate and you have propagation of waves through this plate, the P wave and S wave, they get reflected from both surfaces. And the stress on both surfaces has to be always 0. Because of that, you have a very complex wave propagation inside the plate. What we are looking at is, this is phase velocity, this is frequency times thickness. This is how people normalize it. And you can show that the waves that propagate within a plate, they can only exist on this phase velocity frequency combinations, which are being shown by these modes. This is a little bit, I let it settle in a little bit. So Rayleigh waves are only towards the later part of the frequency times thickness. At larger frequencies, we actually have Rayleigh waves. But if you come here, we have the so-called symmetric and asymmetric waves in a plate. So when you have layered media, the same thing is happening within each layer. So it is a lot more complex than just Rayleigh wave. Dispersion, this is actually the whole dispersion picture, what is happening in just one free plate. So let's break this down and try to understand what this is all about. First of all, we can show that the modes that propagate within a plate, they are a combination of symmetric and antisymmetric or asymmetric waves. And look what that means. So maybe this is easier to look at them here. Symmetric, antisymmetric. Symmetric, so the symmetric with respect to the half plane, like a plane which goes through the half of the plane in the middle, and this is asymmetric. And look at Rayleigh wave in comparison, right? It's only on the surface. So these are called guided waves or Lamb waves, plate Lamb waves. Please give me one second. Tiffany, question.
How is figure B correlated to the figure A? So, like, when do we have this asymmetric?
Yes, I haven't gone there.
Oh, okay.
Let's first look at the concept.
So what do you want?
What is? I'm sorry.
So what are we supposed to take from this? Just that these are.
This is just an introduction. If you please let me develop it, then you will see. So the concept is as follows. When we have waves propagating inside a plate where you have boundaries, the P and S, they get reflected from both boundaries, right? And you have to maintain that here you don't have any stress, And here also you don't have any stress. This coupling of P and S wave kind of combines itself to these plate modes, Lamb waves. So what we are looking here, it's called the dispersion plane. Okay. Rayleigh wave is only one small part of this whole thing, as you can see here. So what are we looking at? Because of this reflection and refraction, we have infinite number of modes inside the plane. We are just looking at now 3 pairs. This goes on this side. Depending on the attenuation, we can have infinite number of modes. What does that mean? It means that at every frequency times thickness, for example here, we can have multiple kinds of waves propagating. So for example here at this frequency you have A0, that's the fundamental antisymmetric mode. And you also have S0, fundamental symmetric mode. But we don't have any other. They all go to infinity here. Now this also can be explained what that means, but okay. Now if we have here, you have different other modes at the same frequency propagating at the same time. Now, what I showed you, the surface wave testing in the past, in the 80s, it has started in the 80s and 90s, and people were ignoring these higher modes. So these are higher modes, A0, S0, A1, S1, A2, S2. For some of you who have come to Dr. Lissenden's students' presentation, I mean, this is the only thing they do. They only work with guided waves. So I hope that after this you have a better understanding of what is going on when you look at what they are doing. So in the past, people kind of ignored the higher modes. So they said, okay, this is the largest amplitude and this is nice. So if you just look at dispersion, you are just ignoring these all other modes. And because of that, a lot of inversion processes were very, very hard to do. So in pavement testing, I don't think you have this, but I explain it afterwards. Let me just give you the significance. So in pavement testing, in 90s, late 90s, beginning of 2000, people started to look at dispersion planes like that. So instead of just looking at the dispersion curve, if we look at the two-dimensional case, we are able to see immediately what are the layering of the system, what is behind. And the process of inversion is a lot more accurate. Now, yes?
What's meant by a guided wave?
I'm sorry?
What is a guided wave?
But these are guided waves.
What does that mean?
That's the waves that propagate inside a plane.
So it's called guided just
because they're guided by the geometry of the system. The nice thing about guided waves is that they can travel a long distance without being attenuated. So they're good if you are looking at one layer of material like composites, where they are not very attenuative, and they can travel a long way without getting attenuated very much. They're being used for pipeline inspection, anything which is long, which has a geometry of a plate with free boundaries and with having boundaries that you have reflection and refraction.
Is this showing B? Is it just showing the 3 different ones that we have simultaneously, or this shows like the evolution of it? Like, do we always have the asymmetric, symmetric, and Rayleigh waves?
You need to look at this picture. I explained that, for example, at 1000, you will have only these 2. But if you go 500, you only have A0, S0. So what this is that for waves propagating, harmonic waves propagating inside a plane, they can only happen at this combination of velocity, frequency times thickness.
So why does it look like the bold line is saying Rayleigh wave velocity?
No, it is approaching. At the end,
Approaching, okay.
this is Rayleigh wave velocity.
Okay.
So in the past, people were just playing with this. But right now, you can also look at the higher modes, especially in materials which are not as attenuated. So we have anti-symmetric, symmetric, anti-symmetric, symmetric, and this can go on. It doesn't stop here. These are just these few numbers. So how do we get to this? If you just use the equation of motion and you impose that the stress on the top and bottom should be 0, you get two very famous equations. So D is the thickness of the plate. K is the wave number. So this is for symmetric. For anti-symmetric mode, this becomes negative. Yeah. And alpha and beta I have to define. So alpha squared is omega squared over Vp squared minus K2. Beta squared is omega squared over Vs squared minus K2. So they come from just by imposing the two boundary conditions that sigma 1,2 equal to sigma 2,2. This is what you had seen for surface wave. So in this case, at x2 equal to 0, are 0, and also they're equal to 0 for x2 equal to negative d. If we consider x1 and x2, like that. It's actually not very hard to get it. If you just substitute for a stress and a strain in a plane strain case and require that the stress is equal to 0, you get these functions. And what you see plotted here is just the solution to this equation. So when you plot the solution to this equation, you get these sets of curves, meaning that only wave propagation can only happen at points which satisfy these frequency, phase velocity constraints in a way. So this is a plot of that. Okay? And then when you explore this plot, you see that they are showing a set of asymmetric, and this is symmetric, and asymmetric modes. And they happen most of the time at the same time. And Rayleigh wave is only one special case where the frequency is so high that, only one surface is affected in a way. If the frequency is lower, then this wave is affecting the entire thickness. Is this becoming more clear? This is more like an introduction. I can't go to the depth, but here, so we can.
Excuse me.
Yes, I know you don't have that. Is that what you wanted to say?
Oh, no. I mean, on the graph shown that, I also noticed there's a 3 velocity name, which is the bending wave velocity,
Yes.
shear wave, and I mean, what do they mean, and how do I differentiate it from each other?
This is flexural mode. So that's what I wanted to explain later. But this is flexural mode, bending wave velocity. That's for low frequency. This is nothing else but the flexural mode that you already know. Now, the asymmetric, it kind of converges at the end towards shear wave velocity. You see, it's a slightly larger than Rayleigh wave velocity, but not quite. So it's going to go there. Looking at the asymmetric wave, it becomes kind of clear why. Right? At the higher frequencies, this is looking like a shear wave velocity. And the same thing here. So it says quasi because this never becomes like a longitudinal wave, but at larger and larger modes, that kind of converges towards longitudinal wave velocity. In one of the examples, this becomes clear what it means. Okay. So conceptually, again, if we look at the, I guess we don't have time to derive anything, but if we look at the displacement in the x and y direction, you see the formulation. So we have a number of cosine and sine terms, and cosine terms, of course, they are symmetric with respect to the center of the plate, and sine terms, they're asymmetric. The point is that the in-plane and out-of-plane motion, they both have symmetric and anti-symmetric components. So look at the formulation. And this is kind of a cross-section to see how the particle motion looks like in plane and out of plane. So a lot of people think that symmetric is in plane. No, they both have different symmetric and anti-symmetric component, and depending on the frequency, it can be more of this, more of that. It's a very complex kind of interaction between P and S wave, guided waves. Now, so people have started saying, okay, SASW, there is a lot of problem with inversion. Inversion is very difficult. If you look at the paper I gave you, there is also a couple of other papers uploaded. You see that a lot of people from long time ago, they were trying to make this inversion process better and better. So one way to make everything better was to really look at multi-channel SSW. That means instead of having only a pair of transducers, you actually have a large number of transducers, as you can see here. And instead of just working with one dispersion curve, you work with the whole dispersion plane. It's actually very easy to do. So one way is to have a large number of receivers at once. The other way is to have just one pair of receiver and source, then you move the source. It's the same thing, right? So the way to do it, just very casually, is when you have the data, like you have here, you just, instead of doing a one-dimensional, what happened again? Instead of doing one-dimensional FFT, you do a two-dimensional FFT. This is fine. So if you do a two-dimensional FFT and you have all your traces, this paper is also uploaded. You can look at the details. You have all these traces. So instead of doing one-dimensional FFT, you do a two-dimensional FFT. Immediately you get here, as time becomes frequency and distance becomes wave number. So you get the dispersion picture immediately after. I don't know, my pen seems to be tired. I thought. Oh, okay, great. So if we do a two-dimensional FFT, which is in MATLAB, it's still one line. Here we get frequency, and here we get wave number. That's kind of a spatial frequency, if you want to think about it. Right? So frequency is like 1 over time. Wave number is like 1 over wavelengths, 1 over distance. And then here is what you get, your dispersion. And this is what you will end up with. So instead of just getting one dispersion curve, you get all these wonderful curves. When you see things a little bit larger, it means that you have larger amplitude here. So let's see what this is. That's a pavement testing. You have the layers here. So we have 3 layers and thicknesses, Poisson's ratios, densities, and velocities. So you see the wave velocity, the Rayleigh wave is 906, 378, and 91. So at the end, for very low frequency, for very high frequency, this curve is converges to Rayleigh wave velocity VR1. This is answering your question in June, what this all means, those things which were written there. So if you look here, the Rayleigh wave velocity, it is changing. So we see the VR2, and then you see that some of the modes, higher modes, they are converging to the p-wave velocity of the first layer at higher frequencies. And of course, at lower frequencies, they are converging to the p-wave velocity of the second layer, etc. So all the information about all the layers is somewhat included in this dispersion plane. However, there is a big deficiency with this method. Can you guess what that is? It's almost, there is no way to understand it without modeling it. I mean, you can see yourself that this is very complicated. So for every kind of test you want to do, you have to have a good forward modeling to understand the dispersion picture that you are getting. Otherwise, no one can really interpret the results. So that's why it's being used mostly for monitoring, not for detection. Because monitoring, you look at changes, right? But if you want to really understand what is going on, and your system is not just a simple 3-layer system, it tends to be very complicated. And you always have to do modeling next to it. You have to model it to be able to interpret all these curves you are getting. It's not as straightforward. So if you find it complicated, don't feel bad about it. Everyone else does. Yeah, this is complicated. Okay, but I just wanted to, I thought you need to know about it because these are the newer developments in the field. SSW is kind of outdated in a way. Any questions?